Welcome back. In this video, we're going to focus on finding derivatives using the chain rule. However, we'll also see situations where we have to use other rules that we've previously learned, such as the product, quotient, sum rule, power rule, derivatives of trig functions. And we have a couple other rules to learn as well, the derivatives of our transcendental functions, e to the x and natural log of x. So exponentials and logarithms are called transcendentals. Here, for this example, we have h of x equals x times the tangent of the quantity, 2 times the square root of x, plus 7. So we've got plus 7. The derivative of a sum, we can take the sum or the derivative of each term. The derivative of 7 will just be 0. So we know that's going to go away. But looking at this is x times the tangent of this. So because that has multiplication in there, we're going to need to make sure that we use our product rule. H of x equals, the first is x, times the derivative with respect to x of the tangent of the quantity 2, and I'm going to rewrite that x to the, or the square root as x to the 1/2 power, plus the tangent of 2 square root of x times the derivative with respect to x of x. And then, as I mentioned, the derivative with respect to x of 7 is 0. So we have a plus 0 here at the end that we do not need to write. All right, so the derivative with respect to x of x, that's just going to go to 1. So that's going to go away. And now we're just faced with having to take this derivative here, the tangent of a quantity, and this quantity, or our argument here, is something other than just x. It's a expression, 2x to the 1/2. So that means we'll use the chain rule. So looking at this, using my chain rule, I'm going to think about that as being the tangent of 2x to the 1/2. Okay, and we need to differentiate that with respect to x. So notice I've used two colors. I have an interior and an exterior, inside and outside. So with the chain rule, this is going to be the derivative of the outside. The derivative of tangent is secant squared. So it's secant squared of that same argument. However, because we have an expression other than x in the interior, we need to take the derivative of that as well. And so this would be times d dx of 2x to the 1/2. So my derivative here, we've got secant squared 2x to the 1/2. And if it so pleases me, I can write that x to the 1/2 back as a square root of x. I'm just converting notation. And my derivative of 2x to the 1/2, that becomes 2 times 1/2 x to the 1/2 minus 1. I'm using my power rule, and that's going to simplify to 1x to the negative 1/2, or just x to the negative 1/2. So I'm going to erase this middle work, and I'm going to rewrite my next line. One thing I'm noticing, I didn't put my prime here on the derivative. So we've got h prime of x equals x. And this value we just found, we calculated that derivative here. So I have x times secant squared 2 square root of x times x to the negative 1/2. And then I have plus tangent of 2x, or 2 square root of x. And then the derivative of x was 1, so that goes away. At this point, we're done with our derivatives. We just need to clean this up. And there's not a lot we can do to clean it up, but I can multiply x and x to the negative 1/2. This is x to the first, x to the negative 1/2. When you multiply similar bases, you're going to add exponents. So this is x to the 1 plus negative 1/2, which is positive 1/2. And x to the positive 1/2, I can write that as square root of x. So I have square root of x, secant squared of 2 square roots of x, plus tangent of 2 square roots of x. And that's my final answer here for calculating my derivative. Okay, so let's do another example. So we're going to do another example which uses trig and the chain rule and the quotient rule to find the derivative. And it actually uses the chain rule twice in here. So we're looking at this function, q equals the sine of the quantity, my argument, that's what we call this. This is the argument, is t divided by the square root of t plus 1. So that argument looks really messy the way it is right now. One thing I can do would be to rewrite this square root right over here as a 1/2 power. And in an effort to eliminate this division bar or get rid of that quotient, I can take this 1/2 power and move it to the other side. That would be a negative 1/2. So I still have my function q here. I'm going to rewrite that as the sine of t times t plus 1. Because of the square root, it was a 1/2 power. Because I moved it to the numerator, I changed that to a negative. All right, so this way, and I could have left it like that, but I would use the quotient rule. And now looking at this, I will have to use my product rule. So we need to break this down into pieces. So we're going to look at our outside. My outside is sine of all of this. So if I am going to find my derivative, the derivative of q with respect to my independent variable t, well, that would be taking the derivative of sine. And the derivative of sine we know is cosine. So it's cosine of all of this. We have t times t plus 1 to the negative 1/2 power. All right, now, if that had just been an x in my argument, we would be done. But because I have a expression with a lot of algebra going on, we also use our chain rule. We're going to take the derivative with respect to our independent variable t of the inside, which is t times t plus 1 to the negative 1/2. So now I'm faced with finding this derivative. And this is t times t plus 1 to the negative 1/2. So we are going to need to use our product rule right here. So we can think about that as a first, and then all of this as a second. So I'm going to do some scratch work for just that piece so I don't run out of space on my screen. So this derivative, that's going to equal t times the derivative with respect to t of t plus 1 to the negative 1/2 plus t plus 1 to the negative 1/2 times the derivative with respect to t of t. And we know that is going to turn into 1 and disappear. So we're almost done. We have one other small derivative to deal with in here. And in this situation, you'll notice we have an outside and an inside. So this is another chain rule. So if I look at this, I have this t here, And my derivative, that's going to be -1/2 the expression to the -1/2 minus 1. And that's going to become -3/2. So my expression on the inside was t plus 1. And because that was something other than x, I come over here and say, well, I still need to take the derivative of that inside, which is t plus 1. And we are left with, pulling this down, I have plus t plus 1 to the -1/2. And again, that was times 1, but we don't need to write that there. So this last piece in here where we need to take the derivative of t is 1, the derivative of 1 is 0. This piece goes to 1, and we don't need to write that anymore. All right, so let's look at what we have. So we've got the cosine of this quantity, t times t plus 1 to the -1/2, all of that times this derivative. And this derivative we just found right here. So the derivative of q with respect to t equals, I have the cosine of t times t plus 1 to the -1/2 times this derivative. And this derivative here is this piece plus this piece. So I have this plus this, which is t, or I'm going to actually say -1/2 t. I've got -1/2 t times t plus 1 to the -3/2. That would be times 1, we said, so we do not need to write that. But then we have that last piece, so plus t plus 1 to the -1/2. At this step, we are completely done with taking any derivatives. Our final steps to clean this up would just be to combine these two terms. And this is just algebra at this point. One thing I'm going to note, that was a -1/2, so I'm going to go and make that look like it did in the beginning. I'm going to put that down in the denominator just for consistency purposes. So the derivative of q with respect to t is equal to the cosine of the quantity t over the square root of t plus 1. All right, so let me rewrite what this piece looks like. That is the same as having -t over 2 t plus 1 to the +3/2 plus 1 over t plus 1 to the +1/2. So we might want to add these two fractions together. And in order to add them together, we'd need to get a common denominator. So this fraction, the second fraction, would need a 2 in front of it, and that exponent would need to become 3/2. The way we can make that is if I multiply by 1, and I'm going to choose to make my 1. We get better at doing this creatively with practice, but I've got 2 times t plus 1 over 2 times t plus 1. And I'm just going to take this and multiply it by this guy, because that will put my 2 in there, and t plus 1 to the 1/2, t plus 1 to the +1, that's going to give me my 3/2. And then if I have the same denominator, I'll be able to add this all the way across. So my final answer here, the derivative of q with respect to t, is the cosine of t over the square root of t plus 1 times -t plus 2t plus 2 over 2 times t plus 1 to the 3/2. Obviously here we can see that negative t and plus 2t, that's just going to give me a positive 1t, so I can combine those. And I just have t plus 2. Erase that to make it look nicer. And if I wanted to take this 3/2 power and make it look like a radical, that would be the same as writing the square root of the quantity t plus 1 cubed. And that's my final answer. So we had a lot of rules involved there. I like to show you those and go over them with you so that you can see my logic and how I kind of unpack the problem and spread it out. So as always, email me if you have any questions. Be sure to reference a video or using the homework, ask my instructor a question that links to the problem you're working on.